Yeah, I'm very happy to be here in Krakow, shortly before Europe shuts all their borders again because of the new Omicron variant. So actually, I was giving this talk, a version of it, last year. It was on this CSP, which is the constraint satisfaction problem. So do many people in the audience know the CSP? I know Michal does. What about the other three? Yeah, some knowledge. By the way, what about SAT solving? Everyone sort of heard of SAT solving? Okay, maybe I reference SAT solving, CSP a bit every now and then. So there's a CSP seminar that was running online during the pandemic. And I gave this seminar there about a year ago, and I've updated it a little bit and I've corrected it. And the seminar title is QCSP Monsters and the Future of the Chen Conjecture. And it's based on the history of QCSPs, as well as a paper that was at Stock last year with Zhuk and me, that was called QCSP Monsters and the Demise of the Chen Conjecture, about how the Chen Conjecture is false in general. But we haven't even met the Chen Conjecture yet, so we have some way to go before we get there. So all this amazing recent work on the Chen Conjecture is really driven by Zhuk. But I've been working in QCSPs some time, and I want to give a sort of flavor of what was going on before Zhuk came into the fray, as well as how he has affected the subject so much. So a quantified constraint satisfaction problem looks a bit like this. The logic associated with it is the logic that just has for all exists, and you can assume it has equals or not, because it's purely conjunctive. You can always propagate out equality, except for some trivial cases. So from the question of studying computational complexity, it doesn't matter whether this logic has equality or doesn't have equality. For the algebraic side, it's better to have equality, so I usually put equality in. So we've got this logic that's fixed, and then we fix a particular structure. Sometimes in CSP, it's called a constraint language, but it's a relational structure, first order relational structure. And we fix it, and then the input is some sentence of the logic, and the question is, does this sentence hold on the model, on the structure B? And basically, this is exactly the same as the CSP, except you've added the universal quantifier, returned the universal quantifier. So an interesting thing about CSPs is they can be defined many ways. They can be defined as a logical problem where the logic is this logic that just has exists and equals. You can define it as a homomorphism problem where you have the structure B is some fixed structure on some signature or in some vocabulary. And then you have another structure A as an input, and you ask whether A has a homomorphism to B. And this is because you can translate any kind of model or structure into a sentence that just asserts the existential quantification of the conjunction of the facts of that model. So the CSP is this amazing problem that has many different ways in which you can view it. You can view it as this homomorphism problem. You can view it as this logical problem. Whereas the QCSP, it really makes sense logically. If you try to view it as a sort of homomorphism problem, you end up partitioning the structure that you started off with in order to make it work nicely, and you get something rather ugly. So you can't quite see my slides here, or can? Yes, they can actually, because my slides are being broadcast without that thing on, I guess. So CSPs are ubiquitous in computer science, and QCSPs are not nearly claimed to be so important in applications. So why are CSPs ubiquitous in computer science? Is it true? I think that finite domain CSPs are quite a broad class, but they don't include that many problems that people are really interested in. They include graph coloring problems, they include satisfiability problems. But most of my interest in traditional CSPs are actually in infinite domain CSPs, where you can phrase lots of problems from temporal and spatial reasoning. And you can also phrase various problems of open complexity in computer science, feasibility problem for tropical programming is an example of one that has a very natural CSP template. Another one, for example, integer factoring, which is not a decision problem, but you can reduce it to a decision problem polynomially each way, that is a CSP, but it's a rather unnatural CSP. So QCSPs, also for finite domains, they have these problems that are reasonably natural. So quantified coloring, quantified satisfiability. But do they have many other natural, are there many other natural problems that are QCSPs? I don't know. Let me make some observations about CSPs and QCSPs. So the Boolean QCSP is actually quite a big problem, quite an important problem. And it has a number of names, either quantified SAT or quantified Boolean formulas. So people have heard maybe of SAT solving, and SAT solving is something that is used industrially now, for example, to verify chips at Intel. They run various verification procedures as SAT solving problems. And in the 1990s, SAT solving was revolutionized by the method of clause learning. And suddenly SAT solvers got a great deal faster. And there hasn't really been a revolution in SAT solving like that since then. QBF is the quantified version of SAT solving. So you can think of the problem satisfiability and exactly its quantified version, quantified satisfiability. Is the problem satisfiability a CSP? Unfortunately, it needs an infinite signature. If you have an infinite signature, it is. 3-SAT is definitely a CSP. And quantified 3-SAT is certainly a quantified CSP. QBF, they say, is now in practical applications going through what's hoped to be a transition as revolutionary for QBF as clause learning was for SAT in the 90s. And it's hoped that QBFs will become a standard modeling language because they can be solved efficiently. Interestingly, in the SAT literature, it's absolutely essential that the underlying formula is in CNF. It's a conjunction of clauses. This is how SAT solvers work. They work on clauses. But in the QBF literature, it's not always assumed that the quantifier-free part of the formula is conjunctive, a conjunction of atoms. Sometimes they allow richer structure because the way the QBF is working is by dependency of variables. It works first on dependencies of variables. So QBF is definitely, I would say, it's a real problem. This is a problem that will in time become industrially important. Maybe it hasn't quite got there yet. The other one is this thing called the relativized QCSP. So the thing about the CSP is if you want to relativize the existential variable, you can always do so. So if you want to say exists X in X, phi of X, you can do this within the language of the CSP because you just say exists X, X of X, and phi of X, right? So you have to have in your language unary relations so you can relativize it. But that's something that can be modeled within a CSP. However, if you want to relativize a universal statement, you have a problem because it looks like this thing here is introducing a negation somehow. It's not in the language, it's not conjunctive anymore. So naturally, QCSPs can relativize their existential variables and they cannot relativize their universal variables. And in fact, in modeling problems, you tend to want to be able to relativize both variables. Now, if you take the version of the QCSP where you can relativize both existential variables and universal variables, you get a different problem from the problem that we're studying today. And you get a problem where the complexity actually has been classified for all structures B, all constraint languages B. And the classification is between those that are in polynomial time and those that are p-space complete. Also, in fact, the Boolean QCSP is classified, and it also has the same classification. Some problems are in P and some are P-space complete. So what's left for finite? I'm only going to talk about finite domain QCSPs. What's left of the non-Boolean QCSP is a problem that I believe to be mostly of interest to theorists, and I actually still would stick by that comment. But when I wrote this survey, I wrote this in a survey in 2017. And at the time, I had no idea that it would be such an interesting theoretical problem. But I hope to make the case today that it is actually a very interesting theoretical problem. So even though it was never such an important problem, perhaps in the literature, not as important at least as the CSP, they were studied a lot in the past by a number of authors, and there are many papers about QCSPs, and they were known to have the complexities P, NP complete, and P space complete. So NP complete we don't have there. We don't have in that other problem, or in the Boolean case we don't have it, but we know we have it in for general QCSPs. Where do we have it? Where do we have NP completeness? Well, okay, the QCSP associated with this structure, which is a three-clique triangle, the QCSP associated with this is quantified three-coloring, and this is well known to be a P-space complete problem. But if we take this graph and we add a new element that's connected, a new vertex that's connected to nothing, so we're considering this whole thing as one graph, then suddenly the universal quantifier is meaningless, because you always evaluate universal variables there. And essentially the QCSP, it degenerates into a CSP. So something that was P-space complete now just has the complexity of the CSP and is NP complete. So these complexities for QCSPs, P, NP complete, P-space complete, are trivial to uncover. And for many years, it looked like they were the only complexities that could exist here, in fact. So here's another way to look at these problems that I found a little bit informative. So the model checking problem is a very general thing. The model checking problem is you're given a structure or a model and a sentence of a logic, and you ask whether that sentence of the logic is true in the model. It's extremely general, much bigger than first order logic, by the way, much bigger than first order logic. But I'm going to look at first order logic. Now, there are many ways to stratify first order logic, or to think of different fragments of it. But the way I'm going to do it is somehow the dumbest way of doing it, the stupidest way. And it's just to think of restricting the symbols. The symbols are exist for all and or not equals. And essentially, you can look at the power set of these, because you've got negation. When you consider equals, you should also think of not equals as a primitive. Probably because you're going to look at duality here. You're going to look at De Morgan duality. So it's an advantage to do that. So you've got this set of things. The set of things is all these things here, and you could consider the power set of this and then try to classify the problem for each element of the power set. And essentially this is something that we did, more or less. We didn't finish it quite. You'll see it's not finished quite. So some of these logics are trivial. So if you just have exists and or, it's trivial. It's always in whatever the structure B is. Whenever the structure B is fixed, the model checking problem is in log space. So for each of these logics, remember my paradigm is that I fix the structure and then I input a sentence of the logic and ask whether it was true on the structure. Notice that if I've got a classification for exists and or, of course I've also got a classification for all and. You know, they're dual by De Morgan's laws. So some of these fragments are trivial. Then some of them are almost trivial. So there are some cases, this first class here was trivial. The second class isn't quite trivial. Some of the problems are in log space, but many of the problems now jump up to maximal complexity, NP hard. Now this row is the CSP. This is the really interesting thing. As I say, it doesn't matter if you have equality or not with exist. Dually, it doesn't matter whether you have disequality with for all. So for years, it was not known what was going on here. Of course, since I wrote this slide, this has been settled. The CSP dichotomy conjecture, the Fedavadi conjecture, was approved, and the proof was first published in 2017. Independent proofs by Bulatov and Zhuk, independent in that they are quite different from one another, but they both follow the algebraic approach. Then you have some other cases that are relatively uninteresting. They just deal with trivial CSPs. Down here at the bottom, we have again some cases where you add lots and lots of expressibility to the logic, where you almost always have maximal complexity. The maximal complexity for first order logic, by the way, p-space. First order logic is always in p-space. Here is something interesting that I worked on 10 years ago. You have positive logic, but you don't have equality. So it's a very strange logic, a very strange logic. It's a logic that's, in fact, seems crazy. Why do we study it? Well, it turns out it has a nice mathematical theory. So even though the logic sounds crazy, its mathematical theory is rather beautiful, and you end up actually getting some complexity. When I say some complexity, what I mean is some complexity in the complexity classification, because you get these four cases: P, NP complete, co-NP complete, P-space complete. So at the time of speaking today, all of these cases are settled except for this Qcsp polychotomy. This is the only one that's not settled. And at the time I drew up this slide, it was assumed the only complexities would be P, NP complete and P-space complete. What we're later going to see in this talk is that exotic complexity classes exist in here. Things like theta 2p, things like dp, things like pi 2p. So in this problem that looks like it should be straightforward, everything is fairly well behaved, we're going to find monsters. These are the Qcsp monsters, by the way, the exotic complexity classes. So this problem, which may not be so important in practice, suddenly becomes interesting to the complexity theorist, because why are we having these exotic complexity classes cropping up here? What's going on with that? So what's the fundamental method that we're going to use to study these Qcsps? It's exactly the same method that has been so successful in studying CSPs. We have two types of structures: relational structures and functional structures. And the functional structures are these things that are called algebras. In universal algebra, they're called algebras. But sometimes I give this talk to people who are not familiar with universal algebra, and then I just say, they're just functional structures. And what's the interplay between relational and functional structures? And here, I don't know how applicable it is today. It's a line that comes from Chan Kiesler's book on model theory. This is the first book that was written on model theory. And Chan Kiesler writes that model theory is logic plus universal algebra. Is that logic only? I don't know. I don't know whether I believe this. It made me think for a while, at least. So what is the interplay between these things? It's this thing called a polymorphism. So when you have tuples that are in a relation and they're drawn here horizontally, you can apply a function, here a k-ary function where there are k rows, and you apply it coordinate wise. And you would say that F is a polymorphism of the relation R if, when you have these k rows above the horizontal line that are in the relation, and you apply the function to them, then the bottom row is also in the relation. And then operations that preserve each of the relations are polymorphisms, and relations invariant under each operation are the invariants. And calligraphic notation is for relational structures. Blackboard notation is for functional structures. So for a long time, it was known that there's something called a Galois correspondence or Galois connection between invariants and polymorphisms. So it's a Galois connection in the sense of Galois' original connection, in that it's a order inverting isomorphism between two lattices. For the constraint satisfaction problem, the correspondence is that inv pol B is exactly what you can define on B in the CSP logic with just exists and equals. And there's a pol inv, there's another side to the Galois correspondence given by pol inv, and it's given by the closure of a set of operations under having projections and composition. There is a similar but more complicated Galois relationship correspondence for the Qcsp, and it involves surjective polymorphisms. So they're surjective in that they cover the range. And then we have that the invariants of the surjective polymorphisms of B are exactly the things that can be defined in the Qcsp logic with for all exists and an equals. So immediately, things are going to get a bit more complicated. The interesting thing about surjective polymorphisms is they're no longer closed under composition. So you can compose two surjective polymorphisms and get something that isn't surjective. You can't do it with unary ones, of course. If you compose two unary ones, you would get something surjective. So if I were to give the other side of this Galois correspondence, which does exist, I would have to say clones, these algebraic objects called clones, but you have to restrict them to their surjective elements, and you lose composition. So already the algebraic approach is getting a bit more complicated. However, I'm going to talk about a version of the Qcsp where I always have all constants. I have constants naming all of the elements. And that's equivalent to having all of these operations that I consider they're idempotent. What does idempotent mean? It means that x comma maps to x. This is the same as an idempotent in a group. So an idempotent in a group is an element such that x plus x equals x. It's the same notion of idempotence. And any idempotent operation is then surjective. So I have surjectivity for free. These two Galois correspondences are the same. In fact, it tells me that the ability to express any relation in the logic for all exists and an equals, it tells me I don't need for all. I could already have done it without for all. And it's actually in that area that I'm going to make my study today, in the area where we have idempotence. And now I'm going to do something controversial. I'm going to mess up the definition of Qcsp. Instead of defining it in terms of a relational structure, I'm going to define it in terms of an algebra. So I'm going to define it in terms of an algebra, and now the input is some sentence that's built with relations that are invariant under that algebra. And then I ask the question, does B model this phi? And the problem is going to arise here because, of course, inv of blackboard B is an infinite set. So I need to be able to encode the relations that are in this infinite set. And here is where I'm departing from the traditional CSP literature, because the traditional CSP literature would say, don't do this. Instead of studying inv B, study larger and larger finite approximations of it. That's the traditional method. So I'm ripping up the rule book and doing something crazy. But I will return to the rule book later. But first, I'm going to do something a bit crazy. Well, yeah, there isn't a simple way to solve it. Traditionally, it's forbidden. You study these finite subsets, because if you want to study it as a single thing, you have to study the encoding of relations. You have to. Okay, now I'm going to move to something that exists in algebra. If I've got an algebra A, then I can study, just like you can study the power of a relation. These powers are direct powers or direct products. Is everyone familiar with the direct product? So if I have a graph like this, then to build its direct product, I have it on two axes like that. And I have an edge there and an edge there. So the square of this graph is two copies of itself. So roughly speaking, you have a relation in G to the K between two tuples that are K tuples, if and only if you have the relation at every point coordinate-wise. And it's similar for an algebra. So if I want to study an algebra, a squared, a cubed, then I build the functions here by applying the functions on pairs. So the elements here are single elements, the elements here are pairs, and you just apply the functions coordinate-wise. So the thing that I'm interested in is the cardinality of minimum generating sets of a squared, a cubed. What is a generating set of a squared? It's a set of tuples, a1, b1, a2, b2, such that when you apply the operations on these tuples, you can get any other tuple. You get the complete set of pairs, for example. And here it's the smallest set, so that smallest set of triples, so that when you apply the operations of the algebra onto those triples, you can get all triples. These are the generating sets. And there are two particular behaviors that I'm interested in here. The polynomial behavior, when the size of the generating set for the ith is just I to the c for some fixed c, and exponential, when there exists some b such that the size of the minimum generating set for the ith is strictly bigger than b to the I. So there's no reason at the moment to think there isn't some behavior in between. So you could have a growth rate of the form b to the square root of I, and that's neither polynomial nor exponential. It's in the middle. So there's no reason at the moment to think that there can't be something in the middle. Although for finite algebras, we're going to learn that there isn't anything in the middle. There isn't anything in the middle. So here are some examples. So Vgold, he's called, you would pronounce it like that in Europe, but his name is Weigold. I think he's known as Weigold. So if B is a finite semigroup, so we're just going to look at algebras that are semigroups. If B is a monoid, then you have the linear PGP, otherwise you have the EGP. So why is it clear that you have the PGP if you're a monoid? If I want to build any tuple, B1, B2, BK, then I just build them. Okay, this is in the language of multiplication that I've got here. So I would build that from the tuple B1, 1, and then 1, B2, and then 1, 1, BK. So I just need to have all tuples of the form B1 and the rest ones, B2 and the rest ones, etc., up to Bn, and to have the permutations of these. So each one of these entries in the row corresponds to n objects because the size of B is n, and there are m of these objects. So the generating set is of size mn, and we have the polynomial generated powers property. Now suppose we're not a monoid. So if we're not a monoid, we will always have this property, this one here, that the size of a coset on an element x is always smaller than the domain. It can never be the whole domain, because if it were the whole domain, because we have a finite set, we would end up with a permutation. And when you take the powers of a permutation on a finite set, you eventually get the identity. So you have this property here, the top one, and you also have the property below it, which is its generalization. So z times b to the m is strictly smaller than n minus 1 to the m. So a subset of b to the m of size r can generate no more than r plus r times n minus 1 to the m elements in Bm. So a generating set must be bigger than this number here, 2n over 2n minus 1 to the m. Remember, n is fixed. The domain B is fixed. So this is proving that you have the exponential generating powers property. So many years ago, there was a guy working in QCSPs called Hubie Chen, and he wrote a lot of papers on QCSPs, and he sort of finished working on the QCSP in about 2012. And then between sort of 2012 and 2018, there were only idiots working in QCSP. And then Zhuck came along and revolutionized it. And there is a prophecy that Chen will return to the QCSP, but we don't know whether it will be fulfilled. So Chen actually studied a number of different types of PGP. One of them is called collapsibility, but I'm going to talk about another one, which is called switchability. So with switchability, the polynomially sized generating set is all tuples that when you read them from the left to the right, they only change elements a small number of times, less than k, for example. So we would call an algebra k PGP switchable if b to the m is generated from the set of m tuples here that only switch at most k times. And switchability was introduced in a slightly different form from this, slightly more complex form. And he introduced it not as an algebraic property, but as a property that would give an algorithm for a QCSP. I shouldn't say that it would make it tractable in the sense that it makes it polynomial time solvable, but it makes it in NP. Remember that the general QCSP on a finite domain is p-space complete. So this magical thing called switchability, it takes the complexity from p-space complete down to NP. And then 6 years ago, we took these two notions of switchability. This notion of switchability is a very straightforward thing to understand. The original notion of Chen that gives this algorithm is more complicated. And we proved that the two things are equivalent. And this proof is a bit convoluted. Actually, Zhuck has recently given us sort of much more user-friendly proof of what's going on here. So this was at the point at which Chen left QCSP, really. Well, he didn't completely leave it, but he was working more on databases and other things. He wrote it in a series of articles dedicated to a birthday of Dexter Cozen. And he wrote a paper called Meditations on the QCSP, something like this. And he thought that PGP and EGP were going to dictate the complexity of QCSPs. He didn't quite phrase it like that. He phrased it like this. He said that when you've got all constants, this is the idempotent case. If you have PGP, then the QCSP is in NP. Otherwise, the QCSP is p-space complete. Note, he doesn't say otherwise you have EGP in the QCSP. He doesn't say that. But actually, in the interim, Zhuck proved in a remarkable work, quite a short work, a very elegant proof, that indeed there is only PGP and EGP, and the only type of PGP is switchability. So Chen didn't know that. Chen introduced switchability because he realized that the thing he had found before called collapsibility wasn't enough. He found that it didn't explain everything. And so he introduced this thing called switchability. And I think it's fair to say that everyone was quite aghast when Zhuck proved so succinctly that actually switchability is the only type of PGP. Since then, Bulatov and Zhuck actually proved the Fedor-Vardy conjecture, which can be given in a number of ways. I'm going to give it this way with all constants, that either you have a particular type of polymorphism called a weak near unanimity operation, and then the problem is in P, and otherwise the problem is NP complete. So let's see how that modifies the Chen conjecture. We could now actually give it as three complexities in light of what Zhuck did in the previous. So either we have PGP and a weak near unanimity, we're in P. Otherwise, we have PGP and no weak near unanimity, then we're NP complete. Otherwise, we're P-space complete. And now I want to talk about the life of the Chen conjecture. And now I want to go back to this setting that I said was crazy, where we have infinite sets of relations. This is something that is never really done in the CSP literature. It's done in the artificial intelligence literature. It's not generally done in the CSP literature. And now there's a problem, because how do you encode relations? How would I encode relations? And there are many ways of encoding relations. The most natural way to almost all people is to encode relations by listing the tuples that are in the relation. Everyone would say that this is the most natural way. So for example, I encode a relation called NAE3, not all equal 3. It's all of the triples on 0, 1, so that they're not all equal. So we don't have all zeros and we don't have all ones. Now, I can write that out in the tuple encoding, or I could write it in Boolean logic with constants on the right-hand side, even actually in disjunctive normal form on the right-hand side. I could also potentially write it with quantifiers. So what are the problems associated with these new things that I'm doing, these strange new things? If I write it out in arbitrary Boolean logic, like I've done on the right, if it were in CNF, then to work out whether the relation is empty would already be potentially an NP hard problem. So there are some problems there, you'd think. If I wrote it out with quantifiers, searching for whether the relation is empty would suddenly become a P-space hard problem. It's a bit crazy. But the thing about today is tractability for me is going to be in NP. The Chen conjecture is about in NP. So NP is like my tractable class. So I'm happy to just have it in that logic on the right-hand side. And I'm going to justify it in the end, because the Chen conjecture is going to hold for that logic, or something like the Chen conjecture is going to hold for that logic, and it's not going to hold for the tuple encoding. But if you prefer to keep polynomial time properties, then imagine that it's in DNF, because DNF satisfiability is a polynomial time problem. Why is the tuple encoding different from the Boolean encoding? Well, this is the 3 not all equal relation. Supposing I've got 100 not all equal relation, listing the tuples is huge. It's exponential. It's exponential in n equals 100, whereas the thing on the right is polynomial. So my version of the Chen conjecture is actually true, and it's this thing in the middle. So you choose the DNF encoding. Actually, this works for any logical encoding without quantifiers, any quantifier-free encoding. You don't need DNF. If you have the PGP, then the Qcsp is in NP. If you have the EGP, which is the only other possibility, then the Qcsp is co-NP hard. So we drop the P-space completes to co-NP hard. And actually, we have to do that, it turns out. There are cases that are in co-NP. And here's another version of the Chen conjecture, which is basically the version with finite approximations to that one. So if you have the PGP, then every finite redux is in NP. Otherwise, there exists a finite reduct that is co-NP hard. So this last conjecture, by the way, is equivalent to the middle theorem under the tuple encoding. They're very closely related, and it's false. It's false. This bottom version with the finite approximations is false. The Chen conjecture with the tuple encoding is false. It has to be with this other encoding. And it's actually only because of this result that I justify a posteriori my use of the logical encoding, because it makes the Chen conjecture true. So what's going on here? Again, to prove this, we're using Joux's machinery. By the way, the PGP parts of this are always holding, right? The thing that fails is the otherwise down here. That's the thing that fails. So for the examples that we consider, we've got these 2 sets. Maybe for alpha and beta, we could always think that we have just 0, 1, and 2. So we've got Alpha is 0 and 2, and beta is 1 and 2. So Zhuk, when he proved that there's only PGP or EGP, he said that if you're idempotent and you have EGP, you can always define a certain relation. And the certain relation that you look at there, it looks like the disjunction of equalities. It's not quite equalities, because they're a bit oblivious to that element. On 0 and 1, they're equalities. And okay, this relation rho this relation sigma is not the right one, but its very close relation, very close relative, close cousin is this relation Tor, which is almost the same. It's very, very similar. And why is this relation Tor useful? Because it's the disjunction of ternary all equal. Well, it's not quite all equal. It's all equal on 0 and 1. It's got problems on 2. And the disjunction of ternary all equal is obviously closely related to the conjunction of ternary not all equal. And the conjunction of ternary not all equal is famously an NP-hard problem. So there's something sort of straightforward going on here. You're going to have Zhuk's method here, and you're going to get co-NP hardness for free, absolutely for free. So you reduce from the complement of this monotone 3 not all equal sat, and it becomes this thing here. And okay, you've got the problem that you've got to encode this relation that you've built. That relation isn't the input for a QCSP, by the way. The input for a QCSP is a conjunction of atoms. That's a new relation. But in fact, in DNF, it has a representation that's polynomially sized in N. Its representation in the tuple encoding is massive. You can't use it. It's nonsense. But because you're cheating with your representations in a sense. You're making it work with the DNF in this crazy setting where the Chen conjecture holds. So already we were wondering whether that co-NP hardness could be improved to p-space hardness. But it can't, because if you just have this set that just has the relations Tor n, it has nothing else, it just has the relations Tor n, then obviously by the previous slide we're co-NP hard, that's clear. But actually there's a co-NP algorithm. You can evaluate all existential variables to something in alpha intersect beta. But this thing here is not a real QCSP, because there's no way to represent this thing, which has an infinite set of relations, as just a finite set of relations, and then close it under definability in the QCSP logic. And traditionally, real QCSPs are finite. They're not infinite objects, they're finite objects. So this is a monster, but it's an abomination. It's an infinite object. It's not a real thing. But actually, any finite redux of this has something called a near unanimity polymorphism. So it's in non-deterministic log space. This is the thing that refutes the alternative Chen conjecture. It's also the thing that explains why the tuple encoding fails. It's the same thing. Okay, so now we go back, we get rid of this madness where we had infinite languages and encodings for infinite languages. We go back to the traditional. We go back to the traditional Chen conjecture, the real thing. Okay, so this version of the QCSP is the more natural version. You don't have an algebra. It's not parameterized by an algebra. It's parameterized by a relational structure. And we just have an input, a sentence of the QCSP logic. Is it true on the structure? So the Chen conjecture, again, we gave its new form. Okay, we can't prove this. We gave up on proving p-space completeness, but could we prove co-NP hardness for the last thing? And actually, it looked straightforward to prove it, very straightforward. All we needed is a result that if these Tor n are definable at all, then they have polynomially computable definitions. Because then we don't need this special representation. We can actually compute their representation and give it in the instance. And I guess many of us thought they did. There should be these they should exist, these polynomially sized definitions. They should exist. And then the Chen conjecture would work. But then Zhuck came along and found some strange things. So here is a language that has two relations. The second relation is some kind of version of and, right? On zero, when you restrict it to 0 and 1, you've got the truth table of and. And the thing above is representing this thing on the right, x not equal to 0 or y equals z. And actually this QCSP, which is obviously a finite QCSP, it just has two relations and the constants. It is co-NP complete. And these examples, actually the first example found of something that's co-NP complete on a finite language like this is involving not just Zhuck, but Olszak. Mirek Olszak is also involved in this. So what's going on here? This is domain 3. We already had a domain 2 classification for the QCSP. Everyone thought the domain 3 classification would just have polynomial time, NP complete, P-space complete. But all the madness is going on here. It's going on when you have these sets alpha here and this set beta here. This is where all the madness is going on. We have EGP here. We have EGP and we have a special polymorphism called the semilattice that maps 0, 0 to 0, 1, 1 to 1, everything else to 2. All of the madness is going on in this region. The classification outside of that region, I think, had been known for some time. And it's in this region that the madness is going on. So this was a bad thing because it showed that you could have these co-NP complete cases, but it's not that bad. Then something much worse was discovered. By the way, this name that I've given R and 2, this is somehow a very bad name. I think I've messed it up. I need to rename this second relation. This is a bad name. It's nothing to do with the AND gate there. This structure is terrible because the polymorphism clone, it's finite structure. Its polymorphism clone has the EGP, but the QCSP is actually in polynomial time. So the QCSP with my other encoding before would obviously be co-NP hard, but the real QCSP, the real object, is in polynomial time. And this is the final nail in the coffin of the Chen conjecture. The Chen conjecture is totally obliterated by this result. It's dead. What's going on here? And then it got even worse because on domain 3, okay, domain 3, the situation isn't too bad because in domain 3, Zhuck was able to demonstrate that there is only these 4 complexities. Okay, there's P, NP complete, P space complete. We knew that, but then there is this co-NP complete. There's nothing else though. There's nothing else. But when you go up to domain size 4, you get something that's DP complete. So DP is this, it's the set theoretic difference of 2 languages in NP. Roughly speaking, it's NP and co-NP. And in particular, you get a complete problem for it, I guess, if you take the take the products of 2 languages, one of them NP complete, one of them co-NP complete, and the yes instances are when there's a yes instance for that problem and a yes instance for that problem. And then things got worse when you go up to the domain of size 10, you get a theta 2p complete problem. What's a theta 2p? It's P with an oracle in NP, but you can only call the oracle a logarithmic number of times. And when we wrote the paper for Stock, these were the only complexities we found. Zhuck has found another monster on domain size 6, I think, that's pi 2p complete. So there's one complexity missing, pi 2p complete there. And actually, Dima thinks they are the only complexities that can be reached. Yeah. So for me, if you can get pi 2p and you can get theta 2p, can't you get delta 2p? Can't you do something there, wiggle it a little bit? So Dima actually believes there's nothing between pi 2p complete and p space complete. And that is perfectly believable. I think he is confident of this. But the fact what there can be within pi 2p, and really, is it just these? This is really interesting. But he has, such an intuition for these problems. So I wonder, in fact, I have no monster for myself, because the monster CoNP complete is really belonging to Olszak. DP complete belongs to Żuk. Theta 2p complete belongs to Emil Jerebek. We found some QCSP in an early draft of the paper, and he wrote to us and said, this problem is theta 2p complete. And we said, what's theta 2p? And then looked it up and then proved it, and it turns out to be true. So Olszak, Jerebek have monsters. Żuk has DP complete and pi 2p complete. So my dream is to have a delta 2p complete monster, but Żuk says it's not there. He says it can't exist. So maybe we could talk a little bit about one proof method, sort of belonging to Olszak and Żuk, and it's a proof that some QCSP is in CoNP. So what's going on here? We have a certain type of polymorphism. Well, we have this semilattice without unit polymorphism. This polymorphism is everywhere in this bad region. This polymorphism is all over it. But we also have another polymorphism, this F polymorphism that's zero stable. So it maps x, 0 to x, and it maps x, 2 to 2. And what Żuk was able to show is that an arbitrary QCSP instance is equivalent to some special pi 2 instance. It's equivalent to some special pi 2 instance that we're then going to solve in CoNP, because we can solve the existential part of it straightforwardly somehow. And you can see that these things at the bottom are somehow successive approximations to the original formula, but where we set some of the elements to 0. So let me see if I can make a vague argument as to what's going on here. So to prove that the top one implies the bottom one, this is the sort of trivial way around. So if we have a solution to the first one, these are Skolem functions that give the solution. Then there's also a solution of the new instance with the additional assignments that we put a number of the x's, the higher x's to 0. And then everything is fine. That's the trivial way around. The non-trivial way around is like this. And this is something that in the original paper actually had a couple of typos in it that were even conceptual mistakes in the writing. They weren't mistakes in the concept. And Dima actually has rewritten this for the final version of the paper. He's rewritten as a formal induction. But I'm going to try to give the idea behind it, what's going on. I think it will still work. So you consider solutions of the new instance where you have these Skolem functions, and f of I depends on x1 up to xn. Now, if by some miracle f of I only depended on x1 up to xi and didn't depend on I plus 1 up to n, then it would be a solution to the original QCSP, which has this interleave structure. If by some miracle that were the case, it would solve the original QCSP. So let n, capital N, be the minimal such that the Skolem function actually depends on something higher than n. And we want to assume for contradiction that such an n does exist and choose it maximal among all solutions. So there's a minimal there, but a maximal here. Now, since f1 up to fn is also a solution of phi n, the following tuple is a solution. So we evaluate x1 up to x capital N at the same, and then we just put zeros. Of course, we've got a solution to this. And these h functions, I've got them depending on x1 up to xn. Of course, they also depend on 0 now, but 0 is a constant. And now we could see this tuple in this way. So you can see that f of 1 only depends on x1, and f up to f of n minus 1 only depends on x1 up to n minus 1. And then it goes a bit bad, right? Then they start to depend on a number of things. But now this is the key trick that Zhuk uses. So he takes these variables xn plus 1, capital N plus 1 up to xn that are appearing in those Skolem functions, and he evaluates them to all possibilities of 0, 1, and 2. And then he applies S. So S is a binary operation, but it's actually associative and commutative. So you can think of it as an Emery operation. He applies that S to the whole lot of solutions that you get there. And then he builds this one solution that has this form. And it has the form that E of capital N, x1 up to n, is equal to C if either it was the only solution that was ever possible, if it's 0 or 1, and otherwise it's equivalent to 2. So it's somehow, if there was any ambivalence in the solution, if it ever changed from one thing, you could always succeed with 2. And of course, if it didn't change ever before, then of course it didn't depend on x capital N up to xn. And then he is applying this H0 polymorphism to these two things to obtain a solution of the instance such that Fn doesn't depend on xn plus 1. And he's violating now the maximality of n. It's a remarkable argument that he is producing here. So what's going on with the future of the Chen conjecture? So the whole of this talk was already in the idempotent case where we had all constants. What about the conservative case, which is the generalization of that, where you have all unary relations? Actually, the Chen conjecture in its original form holds there. In some sense, it's like the biggest sort of obvious class where the Chen conjecture, the original Chen conjecture, does hold. It does hold for conservative languages. Can PGP and EGP be altered slightly to make the Chen conjecture now true again? Can they be modified? Maybe with co-NP hardness instead of p-space hardness. So we'll deal with co-NP hardness, not p-space hardness. But is there a modification? And more generally, can we study other things like a clear condition for co-NP membership? What's the most general condition for co-NP membership? Interestingly, the Zhuk method here, or the Olshat-Zhuk method here, what it's really doing at its heart is reducing something to pi 2. And this is why pi 2 plays such a role. The collapse here is really to pi 2. And Dima believes that he can understand the most general situation in which you collapse to pi 2, because in all other situations, your p-space complete. This is the idea in general. Okay, I'm not talking about Hubert and Hilbert today. But this was from the original. This was from the original talk in the CSP seminar. So what's going on in the future? So yeah. So what are the classifications that you can look at? So I tell you seriously that Dima believes that the full classification for QCSP is a heptacotomy classification into 7 classes, and the only class missing there is pi 2p complete. But this seems quite complicated, maybe even complicated for Zhuk, actually. So maybe to study the problem in a more restricted form, these are the dichotomies in pi 2p versus p-space complete. This is the dichotomy that that Zhuk believes, this one. Another one is in NP versus co-NP hard. This is the dichotomy that needs a new definition of PGP and EGP. It needs a modified definition. Finally, probably the most important dichotomy is in P, the NP hard brackets Turing reductions. So this is probably the most important dichotomy, but it's also the one that we're much too far from. We're not close to getting this one. Much closer to get that one and possibly that one. So maybe I'll leave it there and ask if anyone has any questions.
And algebraic conditions for this Pi-P2 conditions, like candidate or...
He hasn't, Dima hasn't written them down. So something unusual about Zhuk generally as an algebraist, I think this is true. I don't know if Michal can say anything about it. Of all the algebraists I know, he is the one that works most with relations rather than operations. He's really, he thinks very relationally. And his proof here is relational, not polymorphism based. It must, I would think there must be a polymorphism that explains this. And it must be a polymorphism that's not so different, say, from this one, right? This is the one that explains something. So in fact, in the final version of the paper, it's not 0 stable that plays the key role, it's 0,1 stable. So then the polymorphism has the property that fx01 equals x and fx22 equals 2. And that obviously generalizes, but I have no belief that it explains all co-NP membership.
So do you have a condition like relational condition?
Dima has one in his. He hasn't written it up. He has it in his mind.
And idempotency, do you use it only like in your group, because you possibly only the idempotent case. So I know that the Csp is for idempotent. Okay, but is there any other place when you use it?
This classification is not proved in the non-idempotent case.
Yes, but the idempotency.
Because quite a few of the definitions are using constants in the hardness proof, I think. Yeah. So the polynomial and NP cases still hold in the non-idempotent case, but there could be something happening to the other cases. Something strange could happen.
For this Turing reduction, so why is it Turing?
Because you can have co-NP hard as well as NP hard, and you want to treat them both as intractable. But it's strange because the NP cases are explained quite straightforwardly. Well, except for the monster, right? Except for the monster here. This is in polynomial time, but it doesn't have the switchability.